Good evening, sir. Basically, our project is to create an analog multi-output charger with safety protections. The design that we have used delivers multi-voltage DC charging ports. Also, an integrated overheating and short circuit safety features is added in it. Our group consists of 4 members: Afsal, Muhammad Shahul, Muhammad Yasser, and myself, Anas. Our project objectives and core innovations are designing a multi-output analog charger with 5V, 9V and 12V DC outputs, ensuring a stable regulated outputs up to 1 ampere for versatile device uses, implementing an analog safety protection for overheating and short circuit problems, using an NTC thermistor and instant disconnect functions for safety without any other microcontrollers. Coming to our design safety validation methodologies, we can say that by designing power stage regulations and protection separately allows easier troubleshooting and optimization before full system integration. Simulation has been done using LT-SPICE, by which we had identified potential issues early on, ensuring accurate analog behavior representations, and output of 5 voltage has been successfully obtained. Practical assembly on a breadboard test performance across varying load and temperature scenarios needs to be done, which is still in progress. Safety circuits will be rigorously validated by inducing faults to verify rapid response and overall system reliability under stress. Our combined methodology confirms the charger delivers reliable 5V output. System architecture and safety circuit integration. Firstly, an input voltage of 230V AC 50Hz is stepped down by the transformer to a 12V AC. A bridge rectifier converts AC to DC. Filter capacitors are further placed. Further, 3 regulators 7805, 7809 and 7812 are placed, which delivers a stable output of 5V, 9V and 12V respectively. Analog blocks detects overheating and short circuits, triggering relays to disconnect the input. Our output ratings for 5V, 9V and 12V regulated outputs are 5W, 9W and 12W respectively.
Myself Yasser. Now we are looking a quick overview of our circuit. First one, a power stage consisting a 230V AC transformer input. Then regulation stage, we are using IC of 78XS regulator for output. Next is output stage, which will consist of a rotary switch, so we can select our desired output. As we are talking about the protection overview, we have a NTC thermistor for overheating protection and RC circuit trigger relay for short circuit protection. Now we will be discussing technical specifications and safety metrics. Standard input voltage. Input voltage is fixed at 230V AC with a frequency of 50 Hz. Mainly we have 3 output voltages, that are 5V, 9V and 12V. And we have a maximum output current of 1 ampere in each output. We will be maintaining a ripple of 1.06V to ensure clean and noise free power delivery. As for overheating protection, an NTC thermistor monitors temperature, giving a relay to disconnect power if overheating occurs. As for short circuit protection, instant output disconnection via an RC sensing circuit prevents damages during the short circuit faults. As I talked earlier, our input voltage is 230V AC and 50 Hz, and output voltages we are looking is 5V, 9V and 12V DC. Our maximum output current is 1 ampere for each regulator, and our output ripple is 1.06V. Now talking about the fitment capacitor, we will be using a capacitor of 4700 microfarad which will maintain ripple of 1.06 volt and readily available. Now we are looking to the regulator side. We are using IC LM78XS series chosen for reliability, ease of use and internal protection features. For a 12 volt DC steady output, we will be using LM7812, and for a 9 volt, we will be using LM7809, and for 5 volt, we are using LM7805. Also, we will be using a 1 ampere fuse in our circuit. Now we are looking into the block diagram. First, we can see that we have a AC input, then a transformer, then a full wave rectifier, and followed up by a filtering capacitor of 4700 microfarad, and there is a 1 ampere fuse, and now we have a IC of LM7805 for 5 volt output, 09 for 9 volt output, 12 for 12 volt output, and there is a rotary switch which we can switch our desired outputs, and output socket where we can take our output.
Okay, I'm Afsar. Our project is a DC linear regulator power supply. This can give a 12 volt 1 ampere, 5 volt 1 ampere, and a 9 volt 1 ampere output, and we can switch between these values. So the entire circuit, we use LT space to simulate the entire circuit. At first we use a step down transformer to convert 230 volt to 12 volt. Then we use a bridge rectifier to convert pulsating AC to a pulsating DC. By calculating the value of ripple, we use a filter capacitor to rectify to get a linear output. Then we use LM series regulator for getting constant 5 volt, 9 volt and a 12 volt output. Then we use heat sinks to dissipate the heat produced by the voltage regulator.
Now we can look into the technical challenges and analog safety solutions. For overheating detection challenge, we can have a solution of NDC thermistor and relay. It will help to monitor temperature, trigger relay to disconnect output on excessive heat. As we next challenge, short circuit protection, we can implement a RC detection circuit and a relay. This will detect voltage drop, activate relay to instantly disconnect output. For multiple output voltages, we will be using LM78XS series regulators, that is 7805, 7809 and 7812 for our providing stable outputs of 5 volt, 9 volt and 12 volt respectively. As we talked earlier, for our input voltage handling, we will be using 230 volt AC to 12 volt AC transformer. It will step down main voltage to safe level for regulation. As for output ripple reduction, we will be using 4700 microfarad filter capacitor. It will maintain output ripples for stable DC output. And now fault validation, we can use simulated short circuit and overheat testing. It will ensure protection circuit operate effectively under fault conditions.
Hi, myself Mohammed Shahul. I am here to discuss about status of our work done. We have made good progress so far. Initial circuit design and simulation of the 5 volt regulator has been successfully completed, and simulation of the 9 volt and 12 volt regulators are in progress. The next steps we are going to do are hardware assembly and testing of the full system, and also validation of all protection circuits under fault condition. In conclusion, we have a solid design of our analog charger. We are confident in our methodology and look forward to completing the hardware and demonstrating its safety features. Thank you.